Picture this. You're a renowned expert invited to speak to a room full of high school educators who are, understandably, deeply concerned about drug misuse among their students. Before you go on stage, the executive committee escorts you to a private suite and offers you a rather nice single malt whiskey. You drink it, and then you step up to the podium. Well, this exact scenario happened to biopsychologist John P.J. Pennell. As he looked out at that earnest crowd, the sheer irony of the situation hit him like a ton of bricks. Here he was, about to lecture on the dangers of drugs, while actively under the influence of a psychoactive drug himself. It's a pretty fantastic reminder that even our most common everyday social lubricants are, strictly biologically speaking, powerful chemical agents.
Welcome to The Explainer. Today, we're diving into a genuinely fascinating biological cause and effect story. We're going to look at psychoactive drugs not just as social or legal constructs, but as actual biological invaders. We're tracking the complete life cycle of these chemicals in the human body, literally from the second they enter, to the mind-blowing ways our brain defends itself, all the way down to the physiological aftermath of when that drug is suddenly taken away. So, here's our roadmap for this journey. First up, we'll look at the routes of drug administration. Second, the blood-brain barrier. Third, the dose-response curve. And finally, we'll wrap up with the biology of withdrawal. All right, let's jump straight into Section 1. Routes of drug administration, or how the invader actually breaches the system. Because before a drug can do absolutely anything to your brain, that chemical invader has to get inside your body and find its way into your bloodstream, right? There are four main entry routes here. First is oral ingestion, like swallowing a pill or, drinking that whiskey. Second is injection, which just bypasses the digestive tract entirely. Third is inhalation, which pulls the chemical right into the rich capillary networks of the lungs, thanks smoking. And fourth is absorption through the mucous membranes, so the tissues in the nose, mouth, or rectum. Now, the route you choose is absolutely crucial because it dictates not just how fast the drug hits your bloodstream, but how much of it actually reaches its final target in the brain. To really grasp why the route matters so much, let's compare the two extremes. Oral ingestion is basically the go-to for most medicines because it's easy and generally pretty safe. But here's the catch. It is highly unpredictable. The absorption rate can be wildly thrown off by something as simple as how much lunch is still sitting in your stomach. Now contrast that with intravenous injection, or an IV. This drops the drug directly into a vein. It is lightning fast, incredibly strong, and completely predictable. But wow, that speed is a double-edged sword. Because it is so direct, if there's an overdose, an impurity, or an allergic reaction, there is virtually zero time to counteract it. Once it's in, it's in. Which brings us to Section 2, the blood-brain barrier, the ultimate bouncer. You can really think of the blood-brain barrier as the body's ultimate VIP club bouncer. See, in most parts of your body, the cells making up your blood vessel walls are pretty loosely packed. They let molecules pass easily into the surrounding tissue. But in the central nervous system, completely different story. The cells of the blood vessel walls in the brain are packed so tightly together, they form a literal fortress wall. It's a highly protective filter that makes it incredibly difficult for potentially dangerous blood-borne chemicals to cross from the bloodstream into the fluid that actually surrounds your brain cells. So here is the harsh reality for our chemical invader. It frankly doesn't matter how much of the drug is floating around in your bloodstream. The degree to which any therapeutic or recreational drug actually influences your brain activity depends entirely on its ability to slip past that tightly packed cellular fortress. Basically, if it can't get past the bouncer, it has absolutely no chance of crashing the party in your central nervous system. Moving right along to Section 3, the dose-response curve. This is all about the body's defense. Okay, so let's say the drug does successfully sneak past the barrier. What happens then? Well, the brain isn't just going to sit back and take it. The body has to adapt to this chemical intruder, which is a process we call drug tolerance. When you map this out on a dose-response curve, you've got the magnitude of the drug's effect on the vertical axis and the dose on the horizontal axis. Initially, you have a baseline reaction, but over time, with repeated exposure, you actually see that baseline physically shifting to the right. So what does that shift mean for a real living person? It means that if you've built up a tolerance, a significantly greater dose of the drug is required to produce that exact same initial effect. But how does the body actually force that shift to happen? It deploys two incredibly brilliant defense mechanisms. The first is metabolic tolerance. This is where the body launches a counterattack before the drug even reaches the brain. It ramps up liver enzymes to literally break down and convert the active drug into a harmless, inactive form.
The second defense is functional tolerance, and this is wild. This is where the brain itself physically changes. The neural sites adapt by dialing down their own reactivity to the drug. For example, the brain might literally reduce the number of chemical receptors available for the drug to bind to. And when we're talking about psychoactive drugs, the tolerance we develop is largely functional. Your brain is actively physically remodeling itself to resist the invader.
And that sets up Section 4 perfectly, the biology of withdrawal. We like to call this the boomerang.
Because this brings us to the real climax of our story. What on earth happens when this invading drug is suddenly removed from a brain that has completely remodeled itself to fight it? The symmetry between addiction and tolerance here is just brilliant. Think about it. During drug exposure, the drug pushes the system down, right? So the body builds these adaptive neural changes, pushing upward to counteract that weight. Well, when the drug is suddenly taken away, those adaptive changes don't just magically vanish. Without the drug's heavy downward pressure to push against, the brain's upward adaptations shoot right through the roof, manifesting as severe withdrawal effects. And because of this violent boomerang effect, withdrawal symptoms aren't just some random new illness you catch. They are virtually always the exact opposite of the initial effects of the drug. Seriously. If you take an anticonvulsant to stop seizures, withdrawing from it can actually trigger convulsions. If you take a heavy sleeping pill every single night, suddenly stopping is going to produce severe insomnia. Withdrawal is literally just your body's own compensatory mechanisms swinging back violently because the chemical weight they were fighting against is suddenly gone.
To ground this intense biology in something a bit more relatable, let's look at some phrases we throw around every single day. When someone goes through opioid withdrawal, their body experiences intense chills, shivering, and gooseflesh, right alongside severe muscle pains and leg spasms. Those specific, violently opposite biological reactions, they are the literal historical basis for the expressions going cold turkey because of the goosebumps and kicking the habit because of the leg spasms. No joke, it is pure neurobiology woven right into our everyday slang.
But hold on, because the brain's defense mechanisms are even smarter and frankly a lot sneakier than just reacting to the chemical itself. Researchers like Shepard Siegel discovered something called conditioned compensatory responses. It's basically Pavlov's dogs, but for drug tolerance. If you always take a drug in the exact same room with the exact same people, your brain starts to recognize those environmental cues. Eventually, just walking into that specific room causes your brain to preemptively deploy those compensatory defenses before the drug even enters your body, meaning your tolerance is actually situationally specific. You are literally being biologically primed by the physical environment you're standing in. How crazy is that? Which leaves us with a fascinating and maybe slightly provocative final thought. Think about your own daily routines. It doesn't have to be a severe drug. Maybe it's literally just your morning cup of coffee. You walk into your kitchen, you hear the machine, you smell the roasted beans, and your body starts preparing itself. You really have to ask yourself, is your daily habit truly driven by the pursuit of a pleasurable lift? Or has your brain remodeled itself so much that you're simply consuming the substance to avoid the biological boomerang of a conditioned withdrawal? It really makes you rethink who or what biology is actually in the driver's seat.